Hello students, in this video we will apply Rouche's theorem to two problems about approximating roots of one polynomial with another polynomial. So let's recall Rouche's theorem. So Rouche states that if f and g map omega into C are holomorphic, they're holomorphic and C is a simple, regular, i.e. index 1 or index 0 curve that's closed. Regular means closed as well, with mod f of z minus g of z less than mod f of z on C. Then the number of zeros of f are the number of zeros of g inside C. Okay. So here's the first thing we're going to do. We're going to do a perturbation result. So there's a proposition given p of z, which is z to the n plus a n minus 1 z to the n minus 1 all the way down to a0. Given a polynomial with no zeros on the unit circle, then there is a delta, there is such that if all of the, such that whenever bj minus aj is less than delta for all j, we have that the number of zeros of p is equal to the number of zeros of a new polynomial, and that polynomial is z to the n plus bn minus 1 z to the n minus 1 all the way down to b0. In other words, if the coefficients of another polynomial are very, very close, uniformly close within this delta to this polynomial, then the zeros of p and the zeros of this new polynomial are the same. So if I perturb the coefficients of a polynomial by a very, very small amount, right, sufficiently small amount, then the zeros, there'll be no zeros of this function. The zeros of this function in the disk will be the zeros of this function, this other perturbed function. Okay, so here's the proof. So let's consider, so suppose that what? Suppose that, let's do it like this. Q of z is equal to z to the n plus bn minus 1, z to the n minus 1, plus all the way down to what? All the way down to b0. And then estimate for mod z equals 1. So what do we have for mod z equals 1? Let's look at p of z minus q of z. Okay? Well, that's going to be what? That's just going to be a z to the n plus a n minus 1, z to the n minus 1, all the way down to a0, and then minus z to the n minus b n minus 1, z to the n minus 1, all the way down to minus b0. Right? And so what this is the leading term cancels out, you just get the sum. J goes from 0 to n minus 1 of aj minus bj, like that, and then z to the power j, right? Well, this is less than or equal to what? I'm going to have n terms in my sum over here. This is n times the maximum over j of what? The maximum over j of just aj minus bj, right? Good. Now, I want this number over here to be less than what? To be less than the modulus of f, right? So what we can do is, we know by the maximum principle there is a delta tilde greater than 0 such that the minimum on the unit circle of P of z is bigger than delta tilde. Why is that true? This is true since P of z is not equal to 0 on t. That was the assumption of the problem. So what can I say? I can choose if the maximum of this thing over here is less than, so now choose, how do I choose this delta? I need to prove this delta exists, right? Choose our delta to be what? To be, if delta is going to be delta tilde over n, maybe say n plus 1 to make it strict, right? N plus 1. Then I'm assuming that this is less than delta, right? So if we choose our delta to be this delta tilde, which exists by the maximum principle over n plus 1, then we can go back to our proof over here and say this is going to be less than what? This is going to be less than n times delta by assumption, right? And delta is, yeah, exactly. And then delta tilde is equal to n over n plus 1 times delta tilde, which is strictly less than delta tilde, which is equal to the minimum, which is less than or equal to the modulus of P of z on the circle, right? So in other words, P of z minus Q of z is less than P capital of z as long as this delta is chosen to be what? The delta tilde, which is the minimum of that polynomial on the unit circle, over n plus 1 minus the number of terms in the polynomial. So those things are known from the problem, right? And so hence by Rouche's theorem, by Rouche, P of z rather, P of z and Q of z, which is z to the n plus b n minus 1, z to the n minus 1, all the way down to b 0, have the same number of roots in D. So in other words, once I specify a polynomial that doesn't vanish on the unit circle, does not vanish on the unit circle, then if I perturb the coefficients of that polynomial very, 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 very slightly, ever so slightly, for some very small delta, the number of zeros of the perturbation polynomial in the disk will be the same as the number of zeros of the polynomial in the disk, right? So that gives me a real good example of something that's referred to as the continuity of the roots, right? So that's in some sense a continuity argument, right? If the coefficients are close enough, then the number of roots is stable under that small perturbation, right? So it's very much a sensitivity result of the location of the roots of polynomials inside the unit disk. Thank you very much.